And now let me just go for the equations of motion. Okay, for the normal software. Okay. Mm, yes. So what we are going to see, the equations of motion for the normal shock wave. How are we going to define? I mean, so how are we going to derive? Okay. So here, uh, okay. Suppose if you are having the shock wave, yeah, shock wave can be formed only within the confined passages. Okay. So shock wave will be formed okay within the confined passages. Suppose if I am saying that this is your confined passage, okay, then in this you have a shock wave, okay, you have a shock wave. That shock wave you can just say that okay, this is your shock wave, and then what to say? There is a what to say region, okay, non-equilibrium region we can say. That means up to this, up to some okay, before and after the shock wave, there is a non equilibrium regions. So okay, so here it is. Suppose if I say that okay, if I am just considering this away from out of this non-equilibrium regions, say like your pressure flow, okay, flow is taking place, and then after the this one flow, okay. So within this okay region, or if you are not considering the non-equilibrium okay regions, then we can apply the equations, okay, equations of motions, whichever okay we use for other um, okay other process, okay. So then the process equations are, what are the equations I can say? uh, the equations are, first equation I can say is, the first equation is continuity equation, okay, because if you take any okay process or any systems, this continuity equation must be satisfied. So I'm just taking the continuity equation, then this continuity equation you know well, that is nothing but rho 1 a1 v1 equal to rho 2 a2 v2, okay. So this is equation number 1, okay. Let us take equation number 1. Then the second equation will be momentum equation, okay. So let us take momentum equation. uh, okay, so the momentum equation is nothing but just now we saw p1 plus rho 1 v1 square equal to p2 rho 2 square, okay. P2 sorry okay, p2 plus rho 2 v2 square, okay. So this is your equation number 2. Then further the next equation is energy equation, okay. Next equation is energy equation. So the energy equation for the okay, as per the thermodynamics point of view, so energy equation nothing but h1 plus V1 square by 2 equal to H2 plus V2 square by 2. Okay, so this is the energy equation for that means as per thermodynamics point of view, you know well. Okay, that then next thing is by using this all three equations, we are going to find the relationship, okay, for the shock wave. So especially I can say it is for the normal shock wave. That's why we said the equations of motions for the normal shock wave. So by considering this, because we know we said it is like non-equilibrium regions, we can say. So we are not okay. We take the flow properties, apart from this, away from the non-equilibrium regions. Okay, so there you can apply your equations of motions, and we can get the relationship, for the normal shock wave. So then, since these three equations, you have considered, how are we going to solve? So that is the next question. So it means immediately what you have to understand, I have to just make a note of it. If it is for the calorifically perfect gas, okay. If it is for the calorifically for for the calorifically perfect gas, yes. What is the condition? Anyone say? It is nothing but your gas constant. That means characteristics. Especially Cp value. Okay, so that will remain constant. Okay, so your Cp value is will be constant. So when you are saying that it is calorifically perfect, okay, your the Cp value will remain constant. Okay, so then we can say your equations, perfect gas equations, nothing but P equal to rho RT. Then your H, your enthalpy will be equal to Cp into T. Okay, so this is one thing. Then so next thing is what we are going to see. Okay, so that is already we have seen the equations, three equations. One is the continuity, and second one momentum, third one energy equations. By using these three equations, we are going to now find the relationship. So let me just divide the equation, continuity equation, by the momentum equation. You will just see here, I am dividing the equations. That means 1 by 2. Okay, so equation 1 is continuity. Okay, so you can say yeah. Okay, so let me put it. Okay, yeah, you can just say or I'm going to divide not by this 2 by 1. Okay, 2 by 1, not 1 by 2. So okay, it's a 2 by 1. 2 is the momentum equation, nothing but P1 plus rho 1 V1 square equal to P2 plus rho 2 V2 square. Okay, so here, so this is okay. So I am dividing by this. That means left hand side I am dividing by rho 1 V1. That is the continuity equation. That means you know your continuity equation, nothing but rho 1 A1 V1 equal to rho 2 A2 V2. So yesterday itself I made it clear that your area, okay, area across the software will remains constant, okay, because the thickness of the software you know well, okay, it is equivalent to the mean free path. Okay, so since the thickness is very small, so we can just take the area, okay, before and after the software is almost okay same. So in that condition, I'm just using this. Then rho 2 A2, okay, rho 2 into V2, okay. So then further simplification to this, yeah. So what we can do, yes, I can write this can be equal to P1 by rho 1 V1 plus rho 1 V1 square by rho 1 V1 equal to P2 by rho 1 V1 plus rho 1 V, okay, rho 2 V2 square by rho 2 V2, okay. So okay, so I'm just taking this continuity equation, what is there on the left hand side, that means for the subscript to 1, that is nothing but rho 1 V1, and for the right hand side for the subscript 2, it is rho 2 V2, okay. So then further to this, okay, further to the simplification, this will become P1 by rho 1 V1 plus this will be okay cancelling out. We can say that rho 1 cancelled out. V also will be cancelled out. You will have a V1, then that is equal to P2 by rho 2 V2 plus similarly here also rho 2 will get cancelled out, and this is yes, okay. So you will have a V2, okay, yes. So further, okay, we can simplify it. This is nothing but I can say V2 minus V1, okay, equal to P1 by rho 1 V1 minus P2 by rho 2 V2, okay. So this is okay. I can take this equation as the equation number 4, okay. This is the equation number 4, and then further I have to write this one, okay. So we have defined speed of sound, okay. Speed of sound also you know. So speed of sound, that equation is nothing but yes, A equal to square root of gamma RT is common. So if you are replacing in place of RT, okay, so you will have a, that means by using the perfect gas equation, then you will have gamma into P by rho, okay. So this is gamma P by rho, okay. So because perfect gas equation nothing but PV equal to RT. So by using that I have written this. Then what I am going to do, you can write your A1. Suppose see here, A1 square equal to, what is this? A1 square is nothing but gamma into P1 by rho 1. Okay, so this is one thing. Then similarly, I can write A2. A2 square equal to gamma into P2 by rho 2. Okay, so this is one thing, and then yeah, then we can write P1 by rho 1 equal to A1 square by gamma. Okay. Then similarly, you can write P2 by rho 2 equal to A2 square by gamma. Okay. So this is one thing. So we just okay. So this is this we terms. Okay. This simplification we are going to use it in the above equation. That means substituting in the equation number 4, substituting in equation 4. Equation 4. So what we will be getting? Because we know equation 4 is nothing but P1. Okay, so V2 minus V1 equal to P2. So that means yeah, P1 by rho 1 V1 minus P2 by rho 2 V2. Okay, so in this I am going to substitute the this. So it means in place of this value, in place of this P1 rho 1 and these two, I am going to replace. So it will be, if you are replacing, then it will be equal to. Then you can say that V2 minus V1 will be equal to P1 by rho 1, nothing but A1 square by gamma V1. V1 is there, so I am taking as it is. Similarly, you can write it is A2 square by gamma V2. Okay, so this is the V2 minus V1. Okay, so after substituting your speed of sound relationship, so then this further is going to be modified. Okay, or further is going to be changed. So now by using the energy equation, by using the energy equation, so what we are going to get, what we are going to achieve, that is nothing but H1. You know the energy equation, nothing but H1 plus V1 square by 2, that is also equal to H2 plus V2 square by 2. Okay, so this is the energy equation. So in this energy equation, since we have considered the calorifically perfect gas, so we can say that your enthalpy will be equal to Cp into T1 plus V1 square by 2. It's equal to Cp into T2 plus V1 square, V2 square. Okay, so V2 square by 2. Okay, so then you can now modify, okay, or you can substitute the relationship of this one. So because you know Cp equal to what? Okay, so yeah, so your Cp value is nothing but gamma r by gamma minus 1. Substituting this value, okay, in the above equation, you will be getting that gamma r by gamma minus 1 into T1. Okay, so T1 also can be okay added. Then V1 square by 2, that is equal to similarly gamma r T2 by gamma minus 1 plus V2 square by 2 is, I think, okay. So in this we know gamma RT. What is meant by gamma RT? So gamma RT we can write it as yes, It can be written as the a gamma square root of gamma t, nothing but speed of sound. So I can write a1 square by gamma minus 1 plus v1 square by 2. That is equal to a2 square by gamma rt gamma minus 1 plus v2 square by 2. Okay. So this equation we have to modify it. Okay. Also we know that these equations are okay equal to the means we can relate with the critical speed of sound. Okay. So that is nothing but we can write like this. That means a1 square by gamma minus 1 plus v1 square by 2, that is also equal to a2 square by gamma minus 1 plus v2 square by 2, that is also equal to means critical speed of sound. If you consider gamma plus 1 by 2 into this a star. Okay. So because when you see about critical speed of sound, no, so that is nothing but I think gamma minus 1, yes, gamma minus 1 is 1 by 2 gamma minus 1 sorry, gamma plus 1 divided by gamma minus 1 into a star square. Okay. So this relationship already we have seen it. Okay, so this would be not the issue. Okay, so I'm just using this relationship. Okay, so because what is the idea is you may have a h1 plus v1 square by 2 equal to h2 plus v2 square by 2, that is also equal to h0. Okay, so by using that h0 we have arrived to this condition. Okay, that means your critical speed of sound. So yeah, so now we got the relationship between critical speed of sound and okay, your that what to say, energy equations. Okay, modified energy equations. Now this we can rewrite it like this. It can be rewrite as the v1 square. I want what to say, this a1 square and a2 square to be separated. So I am writing a1 square equal to 1 by 2. Okay, when you are taking considering this one, then what happened? It will be like this. So a 1 by 2, 1 by 2 into gamma plus 1. Okay, into a star, that is minus yeah, then I can write it as gamma minus 1 by 2 into v1 square. Okay, I have skipped a few steps. Okay, one step. Okay, before this you can you all can understand this thing, so it is not a very simple task. You can just equate and then you can find out. So okay, then you are getting 1 by 2 into similarly gamma plus 1 into a star square minus gamma minus 1 by 2 into v2 square. Okay, so I think this is okay, this will be clear. Then okay, we are going to utilize this term in the okay, previous equation. Okay, so already that means in the equation number 4, okay, we are going to utilize. So also we know that flow across the soft wave is adiabatic. Flow across the soft wave. Okay, so this is adiabatic. Okay, so now we are going to substitute this relationship. Okay, a1 square and a2 square in the equation number 4. So your equation number 4 is okay. If you are remembering, it correctly. It is nothing but substituting in equation number 4. Then it is nothing but v2 square, v2 minus v1, that is also equal to p1 by rho 1 v1 minus p2 by rho 2 v2. So this we have simplified it earlier itself. Okay, so means we got it something like other relationship. Okay, something modified relationship we got it. So means yeah. So you can see this those relationship. Okay, what we got it. Okay, so we have a v2 minus v1 equal to a1 square by gamma v1 minus a2 square by gamma v2. Okay, so this relationship we can use it here. Means that equation, in that equation we can substitute a1 square and a2 square. Okay, so yeah, so yes, I can write it as this is equal to a1 square by gamma minus a2 square by gamma. Okay, gamma v1 here v1 and here v2. Okay, so we have this relationship, and then now I am going to substitute this in the equation. So your v2 minus v1 equal to that is the left hand side, so that will be equal to let me just take it gamma v1 outside, gamma r v1 outside. Then instead of a1 square, that is nothing but 1 by 2 gamma plus 1 into a star square. Okay, minus gamma minus 1 by 2 into v1 square. So this is a a1 and minus a2. Okay, so similarly 1 by gamma v2 into 1 by 2 gamma plus 1 into a star square minus gamma minus 1 by 2 into v2 square. Okay, so if you see this equation, so what we can do, we can take some terms common. So considering this, okay, what to say, yeah, when you are opening the bracket, okay, when you are opening the bracket, you can just see here. So if you open the bracket, this term 1 by gamma minus gamma v1 will be multiplying with this, and this 1 by gamma v2 will be multiplying with this. Then when it is multiplying with this 1 by gamma v1 is multiplying with the second term, that is gamma v minus 1 by 2 into this. So what will happen here? This will be simplified. Okay, so it's like gamma minus 1, okay, by 2 gamma into v1, okay, into v1. Similarly here also you will get if you are multiplying with the second term, then what happens, gamma minus 1 by 2 into gamma. Okay, so if you want, I will just write it in the one more steps. Okay, so to be understood clearly. Yeah, so the next step you can write the next step can be written as the v2 minus v1, that is equal to, and now I'm just opening the bracket. Okay, so 1 by 2 into means you can say that gamma plus 1 into a star square. Okay, then you have a 1 by this 1 by gamma v1. Okay, so 1 by gamma v1 I will write it as 2 or 2 gamma v1. Okay, this into a star square minus, then you have a gamma minus 1, okay, by 2 into gamma, 2 into gamma into V1, okay, V1. So because V1 there is a V1 square, then we have a V1. So both will get cancelled. One V1 will get cancelled out. Remaining will be V1. Similarly, we can write minus gamma plus 1 by 2 gamma into V2, okay, into A star square minus this minus into minus, this will become plus. So gamma plus 1, sorry, gamma minus 1 by 2 into gamma into V2, okay. So I was talking about these two terms. That means combining combining of these two terms means these two terms can be simplified, okay. These two terms can be simplified. That means I will write it in this way. That means gamma plus 1 by 2 gamma into V1 into A star square minus gamma plus 1 by 2 gamma into V2 into A star square, okay. This is then now what we can do, we can take it out gamma minus 1 by 2 gamma. So that is common in both this. So let me write it as let me take plus sign. So plus into gamma minus 1 by 2 into gamma, okay. Then what is there remaining? Remaining is V2 minus V1, okay. So okay, so we got this after simplification, we are getting this relationship. Okay, means then now this has to be further simplified. Okay, we can just write it in this way. Yes. So even the first and the second term. So now we have three terms. So by combining second and fourth term, we got a third term. Then the first and the second term also can be simplified. Okay, if I do it correctly, means gamma plus 1 by 2 into gamma. Okay, so this also we can take it common in both the first and second term. This is common, so I can take it out, and then remaining will be A star square. Okay, A star square by V1 minus A star square by V2. Okay, into then plus third term. So gamma minus 1 by 2 into gamma into V1 V2 minus V1. Okay, so this is then on the left hand side as it is V2 minus V1. Okay, so this further can be simplified. That means what we can do, even the second, this one, from the V2 minus V1 equal to the gamma plus 1 by 2 into gamma. Then I can take it out the A star square outside. Okay, A star square, if I take it outside, then remaining will be 1 by V1 minus 1 by V2. Then that is plus gamma minus 1 by 2 into gamma into V2 minus V1. Okay, so this further can be simplified. I can just say that V2 minus V1 equal to gamma plus 1 by 2 into gamma into A star square equal, okay, into Yeah. So now what I'm doing V1 V2. Okay, V1 V2 and just then this will become V2 minus V1, V2 minus V1 plus gamma minus 1 by 2 into gamma into V2 minus V1. Okay, so now you can see here one thing. Okay, one common term you can see in all the, okay, throughout the equation, that is nothing but your this. Okay, so this is a common term. This is common term is there here, here, and here. Okay, so this common term we can cancel out throughout the equation. So if I cancel out, okay, this common term, so the remaining will be, yes, I can write it. This is 1 equal to gamma plus 1 by 2 into gamma into a star square. A star square by V1 V2 plus gamma minus 1 by 2 into gamma into, okay, so that is V2 minus V1 got cancelled. Okay, so we also have 1, that's all. Okay, so now keeping this term on the left hand side, gamma plus 1 by 2 gamma into a star square by V1 into V2 equal to 1 minus gamma minus 1 by 2 into gamma. Okay, so this is further we can simplify it. Yes, further if you simplify it, then you will be getting that is equal to, yes, what you will be getting. So by simplify it, gamma plus 1 by 2 into gamma into V1 V2 into a star square equal to 1 minus this, then 2 gamma minus gamma plus 1 by gamma 2 into gamma. Okay, so I'm just getting the relationship, or okay, that means 2 gamma minus gamma, nothing but gamma plus 1 by 2 into gamma. So that is on the right hand side. Then left hand side you have a gamma plus 1 by 2 into gamma V1 V2 into a star square. Okay, so now what we can do, we can cancel out 2 gamma here. Okay, that is there on the denominator. So gamma plus 1 also can be cancelled out. Okay, so gamma plus 1 also can be cancelled out. So that is there on the both side. So now the rest of the term, remaining term is what, okay, we are going to, so remaining term will be, that is equal to a star square equal to V1 into V2. Okay, so this is the thing. Okay, we are getting, okay, after simplification we are getting this relationship. Okay, so this relationship generally we call it as Prandtl, okay, relationship, or Prandtl relations. So it is called as, okay, we can just say if you want, it can be called as the, it is called as Prandtl relation. Okay, so this relationship is very important. Okay, because it is going to determine some of the, one of the important characteristics, or one of the important concept, or one of the important definition which we have defined it for the software. Okay, so what we said, it is nothing like a star square equal to V1 into V2. Okay, so this we can write it as like this. That means we can write it in this way. That means I can simplify it further. A star by V2, that is equal to V1 by A star. Okay. So I'm just writing like this. If you are writing like this, then what will happen? Okay, that is one thing. Or even this can be written like this also. Okay. So it can be either it can be written like this. That means V2 by A star, then V1. Okay, V2 by A star, then A star by V1. Okay, so this is also okay possible. We can write either this combination. Okay, either we can write this way or we can write this way. Both are possible. So I'm just taking it as the second one. Okay, this is only okay feasible one. So I'm just writing it as V2 by A star. Nothing but that is a characteristics Mach number. Okay, so M star we used to say M star. Yes, M2 equal to this is similarly V1 by A1 star. So that also we can say as the 1 by M1 star. So this is one of the important this one. So that means the characteristics Mach number after the shock wave. Okay. So this is okay. M2 is after the shock wave. So if you consider the shock wave, normal shock wave, so this is 1 and this is 2. So your Mach number after the shock wave, okay, is always will be lesser than the what to say this inlet condition. Okay, so the shock wave ahead of the okay, that means Mach number ahead of the shock wave is nothing but M1. Then Mach number behind the shock wave is nothing but M2. Okay, so that here we are getting in terms of characteristics Mach number. So it says that Mach number behind the shock wave is always okay. That means less than the Mach number ahead of the shock wave, that we can say. Or if you say your flow condition, okay, ahead of the shock wave is supersonic, okay, then your Mach number behind the shock wave will be subsonic, because if you take anything, the inverse of that will be okay, always will be very small effect. Okay, so we can say that M2 always okay. So from this only we are okay, just concluding M2 will be always less than the M1. Okay, so that is one thing. And from this, we another understanding is always will be subsonic. If the inlet Mach number is supersonic, then the exit Mach number, it means Mach number after the shock wave will be subsonic. Okay, so Mach number after the okay, Mach number after the shock wave, after the shock wave always will be subsonic. Okay, so this is very important. So even it can be said vice versa also, but later case is not possible. Only in this case is possible. If you are saying M2 star equal to 1 by M1 star, we also can say M1 star equal to M2 1 by M2 star, but that is not possible. Only this is possible. Okay, so in the case of shock wave, only this is possible. M2 star equal to 1 by M1 star. So this condition is possible in shock waves. Okay, but whereas the M1 star equal to 1 by M2 star, that is not okay practically feasible. So we are just not considering this. Okay, so yes, this is important. Okay, so that means Mach number okay after the shock wave